been done over the last couple of years with many people, in particular, let's see when this doesn't work. God, the recording. In particular with Johnny Fay, who did a lot of the analytic continuation stuff, Jianan, who did a lot of the real materials stuff, and Sergei Iskakov, who did a lot of the high performance computing. And of course, all of this is in close collaboration with the group of Dominika Skid, and all the other people that you see here were also involved. Now, this is not a talk about the Hubbard model, right? We have seen tremendous progress in understanding the Hubbard model to the extent that I think that we understand the Hubbard model much, much better than we understand which Hamiltonian we should be studying in the first place. And that led me, not only to write the reviews. You see here, there are actually 2 nice reviews back to back in the annual reviews on that topic of the Hubbard model. But that led me to re-examine, the physics that we're doing here and see to what extent we can take that physics and apply it to real material simulations, real simulations of solids. Now, what is it that we can actually do? Well, of course, we have density functional theory as the workhorse of material science, and it is really an extremely powerful theory, and it is hard to overestimate how powerful it is. It is very good at getting ground state lattice structures and phonons. It is perfect at simulating solids with light elements, Fermi surfaces, band structures, and things like that. And as one of the big successes of that field, we have numerous open source software packages that are readily available for experimentalists, where you essentially can do point and click, and you get a sensible calculation of a band structure for many materials that are out there. That's also the reason why the Nobel Prize in Chemistry was awarded for these theories. Now, what we can do does not exactly line up with what we would like to do. And I want to give you 2 perspectives here for what we would actually like to do. One is the physics perspective, which is that we would like to connect to experiment. And in particular, when we simulate strongly correlated materials, we have materials with V and F electron orbitals. Those are notoriously difficult to simulate with density functional techniques. We're very often interested in finite temperature phenomena. We want to study phase transitions. We have experiments that study not just ground state phenomena, but 1 or 2 particle response functions. Here are a couple of those. We care about transports, and we care about time dependence. And of course, a lot of this is very difficult to capture with standard density functional techniques. I also want to give you the applied math perspective, right? We don't just want to get the right result. We want to get the right result for the right reason. And we want to be able to show that we got the right result. And for that, we need some sort of a priori and a posteriori error estimate that then allows us to go in there, check whether we have the precision to which we would like to solve our model, and then, adaptively refine until we've reached the precision for the observables we actually care about. So we need rigorous uncertainty estimates, and we would also like to have no free parameters. And really, this is the program that Paul Dirac already wrote down in 1929, when he says that it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems. And he concluded this with without too much computation. And of course, that is something that has changed its meaning over the last 100 years. The theoretical framework of all of this is actually fairly simple, right? We consider an electron propagating through a solid. Whenever it encounters another electron, it gets deflected according to the Coulomb law. At least when we have a couple of these processes, we can enumerate them. We can draw fancy pictures. We'll have a couple of so-called diagrams. And in fact, when we have very many of these processes and very strongly correlated or entangled processes, these simple pictures are not enough. But much of the formalism of the theory that was developed in the 1950s and the 1960s remains valid and is in fact known in textbooks. And we have one of the textbook authors, where's Pierce, sitting right there, right, where you can really read back that diagrammatic perturbation theory of the 1960s. That's an easy theory in a way, and we have variants of these theories that we can practically apply. For example, we can do bare low-order expansions, Hartree-Fock, or second-order perturbation theory. We can then use partial summation methods to take certain classes of diagrams that we think might be important, for example, RPA or GW, certain types of ladders. We can sum those up, we'll get a certain result. We can supersize this and say, well, we want to have self-consistent perturbation theories. Once we add self-consistency, we get additional benefits, like in this case, phi derivability or psi derivability, thermodynamic consistency, and the guarantee that we have certain conservation laws, like, for example, particle number and energy respected. But of course, we pick up additional complexity as we go down here. And finally, we can limit ourselves not just to certain low-order diagrams or series of diagrams of a certain type, but we can then use embedded subspaces of non-perturbative summations of diagrams via embedding theories, like, for example, dynamical mean field theory, that allows us to really look at strong correlation problems. And that is the route to strong correlations that I would like to take here. Now, even within those diagrammatic theories, we have a whole bunch of theories that we can choose from, or formulations that we can choose from. We can look at Keldysh diagrammatics, real-time or non-equilibrium problems. We can look at the Matsubara formulation. We can look at real frequency formulations, typically at 0t. We can look at all sorts of different expansions, all sorts of approximations, and all of this gives a wide variety of theories that we could possibly think of implementing in practice. Now, I want to have here a small decision tree that will show you that some of these decisions are theoretically motivated. Some of those are actually practically motivated by the available algorithms that we have for studying those problems. So if we're thinking about weak coupling diagrammatic theories, we could, for example, weak coupling solids, we could, for example, give up on the diagrammatic theories altogether, just study stuff within density functional theory. And that, of course, is very, very successful for weakly correlated materials, but doesn't give you a systematic control over uncertainties and errors. And if we're trying to interface with strong correlation theories, we'll run into all sorts of additional problems, double countings, interactions that we need to guess, downfolding issues, and so on. We could try to go the diagrammatic route rather than the density functional theory route. That here is, of course, much more difficult because we don't have the 40 years of engineering that were put into those nice density functional codes. But once we go the diagrammatic route, even then, we can try to go different ways. We can, for example, go the low-order diagrammatic perturbation theory way. That means, second-order perturbation theory, for example. That does not give us fluctuations. That does not give us screening. So we're actually very limited in the precision that we would get on that route. We can try to take a very good density functional starting point and do some sort of diagrammatic single-shot calculation on top of that. That's a lot of how so-called GW is done in practice. We'll pick up a starting point dependence. If our density functional starting point is not very good, that does not actually get us very far. Or we can then try to do this fully self-consistent, completely forget about any sort of density functional or weak coupling starting point. But if we go that route, well, how do we want to formulate it? We could try to formulate this in real frequency that gives us direct access to spectral functions, but it's almost impossible to close the self-consistency cycle because you have to shift poles. It's very difficult to do this in practice. We could try to go the real-time and Keldysh diagrammatic formalism. Now, this turns out to be very difficult, both theoretically and from an engineering standpoint, but it is actually very promising if you want to do pump-pro. And certainly for small molecules, we can now do that and push this forward. Unfortunately, solids are currently totally out of reach, which leaves the finite temperature or Matsubara formalism. Now, if we go that route and we basically go to finite temperature field theories or quantum statistical mechanics, again, we are going to get great access to energetics and thermodynamics, including guarantees of conservation laws and thermodynamic integrations that are path independent. We have a very easy way of integrating, strong correlation embedding formalisms like dynamical mean field theory or self-energy embedding. The embedding construction really is straightforward because that's the home field of those theories. But unfortunately, whenever we're trying to look at spectral functions, we have an analytic continuation problem, which makes those problems difficult to study. Now, I want to go into this a little bit, but later. But let me just say that this is the route that we're going to take, and we're going to just start doing weak coupling perturbation theory for now, and laying the framework for doing, basically the diagrammatic perturbation theory of the 1960s. Now, in the finite temperature formalism, you have Matsubara frequencies. You can actually compute, if you want to resolve the bare energy scales and temperature in the same function, you need billions of Matsubara frequencies. Now, typically 100 Matsubara frequencies is something we like to work with in the model world. Billions becomes an engineering problem. If we're thinking of a Hubbard U, well, that's just a number. If we go to K-space, it is the same number for all momenta. In practice, we would have a 4 fermion integral. Now, that 4 fermion integral for one of the smallest problems you could possibly think of already gives you about 405 terabytes of storage here. That's quite a bit. Now, again, we are at an engineering limitation, and a lot of the progress in numerics, in compression and so on over the last couple of years has been spent in or invested in getting those types of objects, these scattering vertices and the Green's functions, into compressed formats so that we can actually do practical and controlled calculations with them, so that we can look at real materials calculations. And there's really remarkable behind the scenes developments that make this possible that I'm just not going to talk about in this talk. Now, once we have that, it turns out that a diagram contraction is actually just a fancy tensor multiplication. And fortunately, we have 14-year-old gamers who spend a lot of their money buying GPUs. GPUs are just fancy machines to do tensor contractions very, very quickly. And that means that while a high-end CPU costs you about $4,000 and gives you at most a teraflop of performance, if we're going to one of those GPUs, at the previous generation, we were talking to about 6 teraflops per second on a Volta, about 20 teraflops per second double precision numerics on an Ampere GPU, and about 100 teraflops per second on one of those GPUs that we're having in the current generation of computers for about $10,000. And that means for a typical cluster node, you can now have hundreds of teraflops of just sheer computing power that you can throw at the problem. And that, combined with clever numerics, now makes the theory of the 1960s possible in practice for real solids. Here you see a little supercomputing graph. What you see here is the scaling of the speed up as a function of the number of GPUs. You can see it is almost linear in the number of GPUs. That means we lose very little if we go to bigger and bigger systems. This here is the theoretical peak flop up here, and you see that we're at something like 72% of theoretical peak flop on these machines, which is basically unheard of. The reason for that is that tensor contractions or diagrammatic contractions are really just tensor, lots of parallel tensor contractions that are very efficiently done on these GPUs. And then finally, you can see that this has practical consequences. If we want to do a simple GW calculation fully self-consistent on one of those GPUs, the times to solution here goes from about an hour on a single node down to, a bunch of minutes on, 120 or so GPUs. With that, we can go back, solve GW, which is a conserving theory if you do it self-consistently, and actually show you here that, no matter how we compute the energy, the entropy, or the specific heat, we're actually getting the same value. If you're doing this non-self-consistent, just as an indication here, there's a factor of 2 of ambiguity in the correlation energy in, for example, simple second-order perturbation theory. That makes it very, very difficult to make statements about, phase stability and things like that. All right, with that, we can solve solids. Here's the simple most solid that you could possibly look at. This is silicon, and this is the band structure of silicon as obtained from fully self-consistent GW. You can see this is a total catastrophe. If you show this to an experimentalist, they will laugh you out of the room. They're not going to talk to you ever again. You see that there's possibly an indirect band gap somewhere over here. Maybe they're bands, probably they're dispersing, who knows, right? It's very hard to see anything in here. That's the problem of analytic continuation in practice. Now, even though we have a fully consistent, very nice thermodynamic solution of silicon, and we've made no approximations other than choosing a basis set and limiting ourselves to GW, that's what we're getting. And so back in the pandemic, an undergraduate student who was at Michigan actually looked with me at this problem again. This is Johnny Fay, who did a lot of the work that I'll present to you in the next couple of minutes. The analytic continuation problem is that we really care about the spectral function, which is -1/pi times the imaginary part of the Green's function on the real axis. Now, the Green's function on the real axis is related to the Green's function in Matsubara frequency via this integral equation. In discretize this integral equation, look at it as a kernel inversion. It is an inversion of a very badly behaved, numerically unstable kernel. And if we do that with stochastic methods, you get the pop that I showed you before. However, it turns out that Green's functions actually have a lot of mathematical properties that we are not explicitly enforcing when we're writing this like this. And so I just want to illustrate that if we go to the Lehmann representation and write down a Green's function, we see that there's 1 over a partition function that's a positive number times a square of a number over here times an exponential of a positive number. So all of these are positive numbers. And if we write z equals x plus iy and analyze this expression, we see that we have a Green's function which has a negative part anywhere in the upper half of the complex plane. Now, back in the 1920s, people who worked on complex analysis, in particular Rolf Neven-Linna, who was a big shot in measure theory, worked on complex functions that had positive imaginary parts anywhere in the upper half of the complex plane. Or analogously, if you do a holomorphic mapping, anywhere in the interior of the unit circle. Neven-Linna functions can be mapped one-to-one onto so-called contractive or Schur functions. Schur functions are functions that whenever you apply them, they map the interior of the unit disk to the unit disk, and therefore they suck you towards the center as you successively apply in. Now, Schur, that, by the way, is the same Schur who did the group theory stuff, said that it is actually very easy, given a set of Matsubara points on the imaginary axis, to construct not just one analytic continuation, but every single analytic continuation that is possible that remains causal. And in fact, any Neven-Linna function or Schur function has a continued fraction expansion very close to a Baudet that satisfies the analytic properties of this. And in fact, we can construct every single one of those and then look at them and use them for analytic continuation. Now, why is this a good idea? This is Georg Pick. Georg Pick in 1917 was working on the mathematical properties of these functions. And he said, well, if you take the matrix that has 1 minus Matsubara value times its complex conjugate at frequency j, and you divide it by 1 minus Matsubara frequency times its complex conjugate at, at the other frequency, then that is a matrix. That matrix has to be positive semi-definite. Otherwise, there cannot exist a causal analytic continuation that goes through all of your points. And therefore, if you just take a random matrix and you diagonalize it, you're going to find about as many positive as negative eigenvalues. However, that function space is so restrictive that your interpolating points must all lead to positive eigenvalues. And therefore, the function space of valid analytic continuation is actually very restrictive. And with that interpolation, we can use this to our advantage. That's the outcome. Same data as before. What you see on the left was maximum entropy. This is how we started. What you see on the right is exactly the same Matsubara data. And now with a complex analysis method here, this Neven-Linna analytic continuation that enforces the causal structure of the Green's function. You see very clearly dispersion functions. You see double degeneracies over here, triple degeneracy here at the gamma point. You see that there's an indirect gap to somewhere between gamma and x, and you can actually see the individual bands that are dispersing. These are individual analytic continuation, frequency after frequency after frequency. And the fact that we're getting them, nicely in a nice curve speaks to the precision of the analytic continuation done in that form. Now, with that, we have finally a workable tool to do real material simulations in a fully controlled diagrammatic way, really going back to the 1960s many-body theory and applying those theories to see what is actually contained in them and what can we say about materials. It's actually relatively straightforward to analyze some of these things and to analyze some of the popular approximations that are being done. This here, again, is the band structure of silicon. Measured here or computed with the full Green's function and the full frequency dependence of the self-energy. Now, when we're doing analytic continuation, it's often convenient to just forget about the frequency dependence of the self-energy altogether. That's an approximation. How good is that approximation? Well, it's basically terrible. Now, if we have free parameters in our theory, like a U or a J or a double counting correction that we can apply, we can get away with approximations like that because we just change our parameters until the band gaps are more or less reasonable. Here we do not have that freedom, right? And you can see that we're really, dependent on having precise methods for analyzing these systems. This here is if you're just taking the diagonal part of the self-energy, just the same, you're getting a band gap that is very, very different from what it should actually be. And a lot of the statements in the literature that self-consistent GW is good for energetics, but bad for spectral functions, have nothing to do with the actual self-consistent GW method, and everything to do with approximations that were done after the fact to obtain analytic continuations. All right, so that now gives us a playground with which we can do all sorts of interesting physics. I just want to show you here one of the things that we did recently, which is to not just solve the Schrödinger equation, but actually go to the Dirac equation and solve relativistic systems. That, of course, gives us access to spin-orbit coupling. Now, the way that we usually do spin-orbit coupling in condensed matter is we add an L.S term by hand to our data that gives the splitting that we're observing. What you see here is an ab-initio simulation for a very simple system, silver iodide here, here with a non-relativistic solution, here with a relativistic solution, a so-called X to C1e approximation. And you can see that there's spin-orbit coupling emerging, directly out of the Dirac equation that now allows us to look at topological or spin-orbit coupled systems without any adjustable parameters and in a fully controlled and diagrammatically fully kosher way. Now, with that, of course, we're still at weak coupling. GW is basically a glorified first-order perturbation theory. The second order term, the second order exchange term is missing from that theory. And therefore, you would not expect this to be any good anywhere where you have even weak correlations. And as we're going beyond weak coupling, we have, again, a couple of decisions that we need to take. For example, we could add a vertex correction. Great idea if you're staying at weak coupling and you need to slightly improve your results. Horrible idea if you're in a strong coupling regime, because this here is still being at weak coupling, right? It doesn't really get you into a strongly correlated regime. We could try to add fluctuation channels. We could try to go and, for example, say, well, probably spin fluctuations are important. Let me throw, some sort of magnetic ladder at the problem. I expect superconductivity. Let's throw a particle-particle ladder at the problem. Let's combine all of these and do flex. We can, in fact, do that. We can even do that for realistic systems. However, it is totally uncontrolled, and it's just not a good idea. I don't have time in this talk to go into, how these types of methods fail in practice in realistic systems. So if we want to make progress, then we have to do strong correlation embedding. And that means identifying certain orbitals in which we have strong correlations and adding non-perturbative corrections to those orbitals. We could, in principle, do that with psi functionals, have screen interactions and screen propagators. And that's really what we would like to do. However, we don't have generic impurity solvers that allow us to solve this. And therefore, renormalizing our interactions and renormalizing both our propagators and our interactions, just is a dead end because we don't have the impurity solvers to do it. Unless we're in a high symmetry situation, and then we can do some of this. However, we could, in principle, truncate the orbital or frequency structure. Just say frequency dependence is not important. We're going to take the lowest frequency that is totally uncontrolled. Or we could try to just stay on the level of psi functionals, do the embedding there, have the propagators renormalized, but not the interactions. Now, that is bad because our impurity problems, our strong correlation part, then has to know about very, very large energy scales. And, that we can sort of brute force now with a lot of numerics, adaptive grids, supercomputing, and other things, and then still get results for those types of systems. Now, I'm almost out of time here, so I have a little bit of time to tell you about quantum embedding. The type of quantum embedding that we're using here is what we call self-energy embedding theory. The basic idea is that we have a weak coupling background, like a GW, self-consistent GW solution of the problem. We then identify, based on big quantum chemistry knowledge, the orbitals that we think are strongly correlated. We take those orbitals out and we solve them in a strongly correlated framework that leads to an impurity model, the same way that dynamical mean field theory has introduced that back in 1992. And then once we have that solution, we need to put it back into the environment, adjust the environment so that the environment can relax based on what is happening in the strongly correlated subspaces. For models with local interactions, that then simplifies to dynamical mean field theory. The non-perturbative solution of the correlated subspace corresponds to a solution of a quantum impurity model. QMC, of course, is what we would like to use for the impurity model. Because we have such large energy spaces, that's often not the best type of methodology. And so we have all sorts of other methodologies that are approximate, but often controlled, where we can dial up the correlation strengths, and we see whether our impurity solutions converge or not. And then that allows us to approach the exact limit. For one, it allows us to approach the exact limit by doing the weak coupling part better and better and better by adding more and more diagrams. In practice, that's very hard to do. But it also allows us to approach the exact limit by going to the strong correlation part and making the strongly correlated impurities more and more exact. That, or more and more bigger. And as we're making them bigger, all of the correlations will be covered by the strongly correlated part, and eventually, things will stop to change. The whole thing is fully ab-initio in the sense that if we specify the choice of basis, the choice of weak correlation method, and the basis or the orbitals in which we have strong correlation, we can then actually reproduce the results. I mean, it's diagrammatically very clear, which phi functional approximation we're actually using and how you can reproduce that. I want to conclude here with a couple of examples. This is strontium manganate, a simple perovskite. If we're looking at it within GW, you can see that there is density of states at the Fermi energy. So that's actually a metal within GW. If we then look at what the important orbitals are that might be correlated, we see that this is the manganese orbitals that are over here. Putting those into a strongly correlated subspace immediately will split them away from the Fermi surface, make that thing insulating, and also with the self-consistency, adjust the environment and push the oxygen orbitals away from the Fermi surface. As we then go and gradually add more and more of the orbitals that might be strongly correlated, here in this case, it's various oxygen and manganese orbitals, we can see that, not that much changes anymore, and the system more or less converges. At least within the resolution that we have here, to what it should be and what is measured also in experiment. Here's a different example. This is strontium vanadate. Strontium vanadate is a strongly correlated metal. What you can see here is that within GW, you just get sort of a boring weakly correlated metal. As we add correlations to the vanadium T2G in this case, you get a quasi-particle peak. As you add correlations to other local orbitals like oxygen P's and vanadium EGs and so on, not that much changes anymore. Again, indicative of the fact that these things actually have converged. So with this, we don't have really what I set out to do. We don't really have a control or an a priori or a posteriori error estimate for the types of calculations that we're doing here. But we have a first approach. We have some control over what the correlation is doing. We have a very rigorous theoretical backend of looking at these systems. And we sort of have this dream of a convergence hierarchy where every additional step will get us more and more closely to the quantum solution of that problem. The numerical analysis concept is that the solution provides both an a priori and a posteriori estimate. We don't quite have that. We can add, for example, orbitals. We can add basis functions. We can add correlations and see what happens. That gives us sort of a crude error estimate. And, ideally, we'd have to have an adaptive refinement scheme. And of course, we're very far away from that. But we do have a bunch of hierarchies, not just the system size or the diagram order or the entanglement or the diagram types, the embedding subspace and the basis sets. But with all of this, we can, sort of hope to gradually tune these knobs and get to a correct solution and basically arrive at the so-called Jacob's ladder that some of you might know from DFT, where as you go a step up and up and up in precision, you're getting closer and closer to the exact result. So where do we stand with this? I would say we have a solid foundation to perform many-body theory ab initio without adjustable parameters, reproducibly and accurately, the same way that it's done in the 1960s textbooks. The leading error that we have is actually not the strong correlation error. It is the weak coupling approximation, and all the other approximation like the finite size, the basis sets, the DFT starting point dependence, they're either eliminated or we can more or less have them under control. We can actually do relativity. We can do spin-orbit coupling without adjustable parameter. We can look at excitations. So Neven-Lina theory was really responsible for that. We could show that increasing diagram order is just not a way forward. Just throwing another ladder at it is not a good way of capturing these problems. I haven't shown any data for that, even though it's technically doable, but embedding actually works really well. Dynamical mean field type of approaches here, really seem to capture the right physics and converge to what we want. And, technically this is very expensive to do. The toolkit improves rapidly. And, that is really what provides the non-perturbative component. There are experimental connections at our fingertips. So for example, we have good access to spin correlation functions. We have good access to ARPES and so on, but we still have a long way to go to sort of routine parameter-free calculations, diagrammatic calculations of real materials. And with that, I would like to conclude and thank my group members, in particular, Gianni, who did the Neven-Lina stuff, Jianan, who did most of the calculations for which I showed you a result here, and Sergey, who did a lot of the supercomputing work. Thank you.